Hi, welcome to week 8. We're going to start talking about t-distributions. So over the last 2 weeks, we talked about confidence intervals and hypothesis tests when we have z-methods. This week we're going to introduce t-methods, so we're going to introduce a new distribution. So recap from last week. If we met these conditions that we had taken a sample that was a random sample and was representative of the population that came from, that it was a large enough sample that we could expect the central limit theorem to kick in for that distribution of x bar, and we know the population standard deviation, so this might come from previous studies. A lot of times people will go, okay, this is what we've used in the past and it's worked. So given we know all three of those conditions are met, we can proceed to use these z-methods. So if I want a confidence interval, it's x bar plus or minus some critical value z star times sigma of the population over the square root of n, which is the same as if you want to condense and say sigma of x bar. If you wanted to test a hypothesis, you would calculate a z-test statistic. So you would take what you observed minus what's claimed over the standard deviation over square root of n. So all of these, so once you get this, it means that you use that z table, that z distribution, to get your p-value. Here you use a z star. So these are z methods. That's why they're z methods. So more realistic, a lot of the times we really can't assume that the population is normally distributed, which can be really difficult. Usually the way we try to tell how the population is shaped is by plotting the sample. Because if the sample is representative, then how the sample is roughly shaped should be roughly how the population is shaped. So central limit theorem, as long as the sample is big enough, we should be okay. But the key difference between the last 2 weeks and this week is we usually do not have the opportunity to know the population standard deviation. We usually just don't have access to that information. So I found this one. Surprisingly, I didn't have to make this. Mr. T test. I pity the fool that doesn't know their population standard deviation. So the problem that we're going to use in the next, like this lesson and the next few lessons, we have a car manufacturer. They make some sort of sports car, and they want to estimate the average annual mileage for all the drivers of the sports car. Probably, obviously, like these are very, very linked to things like warranties. You want to know, well, okay, if we give them this many years, how many miles are they going? How much might we expect them to go on average? So they want a 95% confidence in the estimate. And they want to assume, we're going to assume the population is normal. So they take a random sample of 10 drivers and they get the following. So like this is driver 1, they drove 11,501 miles in that year. Driver 2, 8,987, and so on, and there are 10 of them. So it's good that the population is normal because a sample of 10 is not very big. So when we go to check the conditions, absolutely, it was a random sample. That's great. Although I'm not really sure how they decided to select all of the, who that master list was from. And then, is the sampling distribution normal? Yeah, because we do have a normal population, so a sample size of 10 will be big enough. But then, do we know sigma of x? So, do we know how it's spread in the population? Because if we want to calculate a confidence interval, this would be our equation here. But we don't know. If we don't know sigma, we can't plug in sigma. So the idea is if you don't know sigma, you shouldn't be using a z star. No sigma, no z star. So we are going to be transitioning over to one sample t methods. So their conditions are going to look very similar to the last 2 weeks. So we still want to have a representative sample, usually a random sample from the population, we still want our sample to be big enough so that we could expect that the sampling distribution is going to be roughly normal. However, this is what's different, is condition 3. So we do not know the population standard deviation. However, we can estimate it using the sample standard deviation. So it's kind of like the next best thing. We can use what we have from our sample to estimate it. And so remember, this is just way back, one of the first couple of weeks here, where's that sum of, and we're not going to be calculating this by hand too much, but just to remind you of that equation. There you go. So when these conditions have not been met, there are other methods we can use. We have things like non-parametric methods, we have randomization methods. We're not going to cover them in ST201, but just know that we pretty much, this is a backup to those first set. If I don't meet all the conditions, for example, I don't know the population standard deviation, and then I don't meet the conditions for the T methods, there is a backup method for that. In fact, in stats, it's kind of like a running joke. Almost everybody is eager to create a best backup method because they almost always seem to name it after themselves. So once again, you're not responsible for knowing these backup methods, but just know that if we don't meet these conditions, there are other ways that we can calculate confidence intervals or perform hypothesis tests. So here we're going to start talking a little more like standard error. So we kind of introduced the idea when we talked about hypothesis tests and confidence intervals before. So here we're going to estimate the population standard deviation by using the sample standard deviation S. So recall, this is if I wanted to find the standard deviation for the sampling distribution of x bar, it's sigma of x over root n. However then, so if I want the standard error of the sample mean, notice now it's an S instead of sigma. So in other words here, sigma of x bar equal to sigma of x over the square root of n. This is approximately just the sample standard deviation over the square root of n, which is the standard error of x bar. So the previous 2 weeks, we used what was on the left. Now we're going to be using what's on the right. So that means that we actually, if we're going to use that particular, like S over root n, we have to use T distributions instead of our Z normal distributions. So here, our distribution is roughly normal when standardized with, so this is what we were doing the last couple of weeks. So my Z statistic is what I observed minus what's claimed over sigma of x over root n. But when I don't know that, I'm going to have S of x instead of sigma. So note, this is the key thing that's changed here. All of the rest of the equation is the same, except now it's a T test statistic. So when I had a Z test statistic, I used a Z table. Now I'm going to use a T table. And you can look at the shapes, they're very similar. That T distribution is a tiny bit wider. So they are, the T methods, they're extremely common. I would argue they're probably more common than using Z methods for a mean, because it's very rare that we actually get to know what sigma of x is in real life. So this is going to look very, very similar setup to last week. So if we don't know, only if we don't know sigma of x, we will use a t-stat and we'll have s instead of sigma. And once we have our t-test statistics, so you go ahead, you plug in the numbers, you get a value, then you'll go to a t-table and you'll be looking at specific degrees of freedom. So the degrees of freedom tells us like how wide or narrow the distribution gets. So our t-test statistic, it's going to have degrees of freedom, whatever your sample size is, -1. So if you have a sample size of 20, your degrees of freedom are 19. So as long as we're doing it set up this way, that's going to be our degrees of freedom every time. So then what does it tell us? The t-test statistic is very similar to the z-test statistic. It tells us how many standard errors. So instead of standard deviations, that x bar from our sample, so what we actually observed, is from the mean of the distribution, mu of x, or how far it is from the claimed mean. So how many standard errors above the claimed mean is what we actually saw in our sample, or how many standard deviations below, because it can be less than. So t-distributions, they are very, very similar to normal distributions. They're perfectly symmetric, so if I were to draw a line down the middle, fold it in half, and it's exactly the same on both sides. It's centered at 0, like the z-distribution, and it goes on forever in both directions. So even though we tend to not draw it further out than like 3 or so, like it goes out forever. So it's very similar, like it's kind of a bell shape, and how like tall / wide it is kind of depends on the degrees of freedom. So that's going to matter like how big your sample size is. The lower your degrees of freedom, the wider your distribution, and a little bit shorter, versus the higher your degrees of freedom, narrower at the ends, and then taller in the middle. So as your sample size gets bigger and bigger, you can see here, your t-distribution is going to get closer and closer to the z-distribution. So as you go to infinity, of course you won't ever quite get there. Your t-distribution is going to be really, really close to a z-distribution. So the way I learned it is the t-distribution has fattier tails, so it has thicker tails. So here the z is this blue. You can see there's more area in the tails here, which means it's shorter in the middle a little bit. And we use this for a lot of estimation hypothesis procedures. So the degrees of freedom, it kind of comes down to, if I know the sample mean, and I know if I have a sample of, say, 20 observations, if I know 19 of those observations and I know the sample mean, I have enough information to find the 20th observation. So I only have 19 degrees of freedom. That's what it comes down to. So here, just know we use n-1. More complicated tests might have slightly different degrees of freedom. We're going to stick to n-1. So using z methods versus t methods. So both of them are for if you want to make a statement about the mean. So do you want to estimate it? Or do you want to test it? Maybe there's a claim that you want to test it against. It all comes down to whether or not you know sigma of x. If you know sigma of x, go straight to z methods. Absolutely. Z methods is our preferred choice. We will always pick z methods over t methods if you know sigma. And that's the big fat if. T, if you don't know sigma, you're going to go ahead, you're going to use the sample standard deviation from the sample, and this is going to be t methods. So if you're reading a problem and it only has sample data, so they go ahead, they tell you the question that they have, and they only give you information from the sample, or at least they don't tell you a value for sigma, you should be going straight to T methods. So in general, like for both of these scenarios, you could always use T methods. However, you are going to increase usually your type 2 error just a little bit if you use T methods when you could use Z methods. So just know, if you know sigma, go straight to Z. Z is our favorite. If you don't know sigma, you have to use T. Okay, and that's it for lesson 28. We're going to get into running a confidence interval and a hypothesis test using T procedures.